Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hello students, good morning. So today we are, as you know, I have started group 30 chemistry of group 13 elements, and I have explained few basic things. Now we are going to study about some important compounds of boron, and mostly the compounds of boron that we are going to study about is the borax, orthoboric acid, or the boric acid we also call, and the diborane. These are the three compounds that are there in our syllabus. So let us first start with the borax, and borax structure you can see here. This is the structure of the borax with 8 water molecules as the water of crystallization. So those are water molecules, 8 water molecules are not shown. The chemical formula of borax is Na2V4O7 10H2O. What I am saying, 8 water molecules as a water of crystallization, but in the chemical formula I am writing is 10H2O. What does it mean? Am I making any mistake? So the answer is no, I am not making any mistake. And the reality actually this compound borax is the has a tetranuclear unit, and if you see this structure, this B4 boron atoms are there, and between all that they occupy 4 corners. If you want to write the structural formula of this, so these 4 boron atoms, they occupy 4 corners, and each of the boron atom like this, other than these two. So now all the corners, they are connected by one oxygen atom. So there is a BO linking. So B oxygen is between this boron, one oxygen is between this boron, one oxygen is between this boron, one oxygen is between this boron, and there is one oxygen which is there in the diagonally opposite boron. In one case only, not here. Here there is no OB bond extra, that is on the diagonal side. Here there is only, in this case, the diagonal BOB bond is there, and because of that, now you can see here this boron has a negative charge. Why this negative charge is there? Because boron has it has only 3 electrons in its outermost shell, and it can form only 3 bonds, covalent bonds, and that you can see here in this case. This oxygen is sharing one of its electron with this boron, so there is one single bond. This there is one single bond, and there is BOH bond. This is OH group, so there is one BOH bond. Now, if you want to make another bond, so another bond can be formed only if O minus donates its lone pair of electrons to this boron and any of this boron, and so this is actually this is O minus, O double minus, and O2 minus is oxide. It is giving one of its electron to this and one of its electron to this. This way you can understand, although this is not oxide, pure oxide that we see in the case of ionic compounds, it is, but this is a kind of its oxidation state. You can see is -2 in all the cases. So this is in a way O minus, and that O minus is actually we see in the case of boron, because boron, its electrons, it gives 2 electrons to this boron, and so this boron will have -1 formal charge on it, and only that in that case it can have 8 electrons in its outermost shell. So this boron has a complete octet, this boron also has a complete octet, and these two borons, they do not have complete octet. There is a sextet of the electrons in these two borons, and each boron atom is also linked to one OH group, and this OH group you can see here. Or another way, one you can see this is no, but for these two cases you may see this is a OH minus group, but that is also there. And even now the 8 water molecules has a water of crystallization that are there. And actually what I said, this is tetranuclear unit, and in tetranuclear unit what you see, B4O5. So B1 2 3 4 and O5, two oxygens, two oxygen and one oxygen, O5 and OH4 minus, and this OH4 and 2 minus charges, one on this boron, one on this boron, that we see here. And you don't have to remember why which boron should have a negative charge, because the valency and the understanding of valency itself will tell you which boron will have a negative charge. And so these two, because whatever it's ideal valency in the neutral state, if the valency is 6, the in the neutral state it will have 0 charge, formal charge that we see here. And if the valency is 4 in the case of boron, it means boron has acquired some negative charge. These things happens in the case of nitrogen. If the nitrogen is there, if the nitrogen has 4 covalency, it means one of the lone pair of electrons is involved in somewhere. It means the nitrogen will have plus charge, because nitrogen, if it is there, 8 electrons only there, so nitrogen will have a positive charge. And between boron and nitrogen there is carbon, and that we know carbon will have a complete octet accordingly, like in the CH4. So the boron, if boron's octet is usually completed, it means the boron will usually have a negative charge, and nitrogen in such cases it will have a positive charge, like ammonium ion, those things we know. So the borax is the most important compound of boron, and that means the borax dissolve in water to give an alkaline solution. So this equation that we know, this reaction, so this is the borax Na2B4O7 and 10 water molecule you can just write, plus 7H2O. When it reacts with the water, it gives alkaline solution as per this formula. So this NaOH will be formed. NaOH is being formed because of the hydrolysis of the water, and now this is the boric acid, or we also call the orthoboric acid. The 4 molecules of orthoboric acid and 2 molecules of NaOH, the base is formed. Now one can ask a question here. The 4 molecules of an acid is formed because the name we are writing orthoboric acid, and 2 molecules of base is formed. So usually number of acid, the molecules of acid is more than the number of molecules of base. Then how come this solution be alkaline? One should expect, and that also this boric acid has 3 hydrogens in it. So the why should this solution be alkaline? The answer is this orthoboric acid is not a protic acid. It doesn't provide proton from itself. It will not be ionized into H plus and HBO3 minus. However, it is a very weak acid, very weak acid, and it, as we know, the boron, this is a B OH OH OH. So there are 3 BOH bonds in this case, and so the octet of boron is not complete in this case. And if the octet of boron is not complete in this case, and if you put this orthoboric acid in water, so one water molecule will attack the boron center, and because the water molecule has a lone pair, and so OH minus will now water molecule will split, and that we call the hydrolysis, and the water molecules will split into OH minus and H plus, and that H plus is being released, and that we call, that is why we call it as a acid. But that reaction, as we know, this is a not very facile reaction, and the equilibrium constant is very less for the what the ionization of boric acid, means the formation of hydrolysis of boric acid. That reaction's equilibrium constant is very low, and that's why this orthoboric acid is a very weak acid. And this acid, as you can understand here, it's not a protic acid, but it's a Lewis acid, because boron has a sextate and it has a vacant orbital, so it can accept OH minus ion from the water molecule, from the auto ionization of water. And so, and we know in the case of NaOH, it's almost 100% ionized. So, 2 molecules of NaOH both are 100% ionized. And here, although 4 molecules, but only few molecules out of the Avogadro number of molecules, only few number of molecules, certain 100,000 or something, will be taking part in the hydrolysis of water. And so, this orthoboric acid is a weak acid, and a strong base. So, the solution is alkaline solution. Now on heating, borax first loses its water and swells up. So once the borax Na2B4O7 10H2O, if we heat, what happens initially, these 10 water molecules will be gone away. So once these 10 water molecules will be gone away, so Na2B4O7 will be formed. Na2B4O7 is formed, and on further heating, this Na2B4O7 means the anhydrous borax. So anhydrous borax, on further heating, it gives sodium metaborate NaBO2 plus B2O3, which is boric anhydride. This we call boric anhydride, boric acid. If we remove water molecule from that, so it's anhydride of, so this is the boric anhydride, we call this molecule B2O3, and this sodium metaborate. Now the metaborate of many transition metals, and this reaction is very important because this is reaction is important in the borax bead test, and the borax bead test that we will study later on. So the metaborates, what are the metaborates? This is sodium metaborate, this is the metaborate NaBO2. The metaborates of many transition metals have characteristic colors. Therefore, borax bead test can be used to identify them in the laboratory. Because different transition metals, when they combine with this metaborate, means they form metaborates, they show different colors. And based on those characteristic colors, one can identify which metal it may be. So, for example, when borax is heated in a Bunsen burner flame with cobalt oxide, on a loop of platinum wire, a blue colored COBO2 twice, this is the cobalt metaborate bead is formed. So, cobalt metaborate bead of cobalt metaborate, which is blue in color, so one can understand this is the cobalt, the transition metal is the cobalt. So, on heating, borax first loses water molecules and swells up, and after losing water, it swells up. On further heating, it turns into transparent liquid, and that transparent liquid is solidifies because the liquid was already transparent. On solidification, that material, the solid material, is also solid, and that is why we call into the glass-like material, because we know the glass is transparent, and so this glass-like material known as borax bead, and this is the borax bead that we call sodium metaborate. And now let's look into the orthoboric acid. So orthoboric acid or the boric acid. The formula is H3BO3 that we have seen here as well. H3BO3. So H3BO3 is a white crystalline solid with soapy touch. Soapy touch it has, and it's H3BO3, and it's sparingly soluble in normal water or the cold water, but is highly soluble in hot water, orthoboric acid. We prepare the preparation of base orthoboric acid can be prepared by acidifying an aqueous solution of borax. So borax we know Na2B4O7 10H2O, and if the dilute acid if you use acidifying water, so 2HCl plus 5H2O, because the dilute acid that is already there, acidifying an aqueous solution, it means the borax is there, you just add aqueous solution of an acid, and you will get the this orthoboric acid, the four molecules of orthoboric acid or BOH thrice, as I said, this boron and OH thrice is formed. This is orthoboric acid, or you can write H3BO3, and two molecules of NCl will also be formed. So this Na and this Cl will go here, and this H, this hydrogen, and this is H2O. So hydrogen, when one hydrogen reacts with water, so what will happen? Two OH groups will be formed, and those OH groups now is combining with the boron, and this way this formation happens. So it is also formed by the hydrolysis reaction of most of the boron compounds. So orthoboric acid, what does it mean? It also formed by the hydrolysis of the most of the boron compounds, particularly boron halides and boron hydride. Both of the reaction for the hydrolysis of boron hydride we will see later. Boron halide is reported here. So BX3, this X could be chlorine, bromine, iodine. So the chloride, bromide, iodide. So BX3 plus 3H2O, it gives BOH thrice plus 3HX. This is a direct displacement, double displacement reaction kind of thing. So X is replaced here with the OH group of this water molecules. The OH of water is replaced with the X. So this is exchange here, this is gone here, and X has come to hydrogen. So the HX formation and BOH thrice formation happens. The structure of, if you look at the structure of the orthoboric acid, as we know, this orthoboric acid is sp2 hybridization. If you just look at this structure, this is BOH thrice, and BOH thrice, what does it mean? It means three sigma bonds are there. There is no lone pair, and three sigma bonds with the no lone pair using VSEPR theory. We can say that, and in the valence bond theory, sp2 hybridization will be there, and sp2 hybridization triangular planar structure will be formed. And so the triangular planar structure you can see here, the BOH, 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 this. So all the BOH thrice atoms are these are planar, and since OH moieties are there, three OH moieties are there, which has potential to form hydrogen bonds. So that this boric acid, these molecules are they are highly associative because of the hydrogen bond formation, and you can see here the hydrogen bond formation between different boric acid molecules. So this is the orthoboric acid, one unit of the orthoboric acid. So now this OH is forming hydrogen bond with another OH of the another boric acid that is shown in the green color in this case, And now we can see this oxygen can also accept one hydrogen bond from the another boric acid molecule, and that we see here. So in that case, what we see here of the central, the one boric acid can have maximum up to 2, the 6 hydrogen bonds it can form. So one boric acid can form 6 hydrogen bonds, and because of the 6 hydrogen bonds, all the molecules are planar. These hydrogen bonds are also planar, and so this there is a sheet structure that we see, the formation of a sheet structure of the boric acid, and these sheet structures they may be arranged over these different sheets over one another. So the boric acid has a layer structure in which planar BO3 units are joined by hydrogen bonds, and that we see here in this structure. The boric acid is a weak monobasic acid. As I said, it's a weak monobasic acid. It means it will, on dissolving in water, provide one H plus, and that one H plus, though it is a monobasic acid, but that H plus is not the H plus of the boric acid itself. That H plus comes from the hydrolysis of water, and so that H plus belongs to the water molecules or to the solvent water. So it is, the boric acid is not a protonic acid or a protic acid, as I said earlier. It's actually a Lewis acid. Lewis acid, and it behaves by accepting electrons from the hydroxyl ion. And in, we know that because of the auto or the self ionization of water molecules, water contains OH minus and H plus ions, though in a very low concentration. But OH minus and H plus ions are there, and these OH minus ions are actually Lewis bases. They're Lewis base, and they can actually interact. They have a lone pair of electron. The oxygen octet is also complete, and now it can put its lone pair of electron into the vacant p orbital of boron, and so this BO is thrice you can see here. And the water molecule we can just consider here, because once the OH minus is occupied with this, involved with this, the H plus ion, free H plus ion will be there, because one H plus ion and one OH minus ion can be formed by the self ionization of water. If OH minus makes a covalent bond with the BOH thrice the boric acid, we have one H plus ion free in the extra, and so this we can see that the monobasic character comes from that. So then general reaction we can write BOH thrice plus 2HOH. This is a water molecule, and this water molecule, this OH minus group will go here, and this OH minus group will go. The OH minus group will go, so there will be negative charge on this, and two water molecules. So one water molecule will still be there, and H plus of from the one water molecule, which is splitted into OH minus and H plus, and that H plus has gone to the another water molecule. That's why two water molecules are taken here, and so we see the formation of the hydronium ion. And even you can write this equation just by just taking one water molecule, but in that case here you have to write H plus, not H3O plus. So on heating above 370 Kelvin, orthoboric acid forms metaboric acid, and metaboric acid is HBO2, which on further heating yields boric oxide B2O3, or boric anhydride we also call. This is a boric oxide or boric anhydride is formed. So H3BO3 is a boric acid plus HBO2, sorry, H3BO3 on heating it gives HBO2, which we call the metaboric acid. HBO2 is what? It's a metaboric acid, and the metaboric acid it is formed when one water molecule is removed from the boric acid. So one water molecule is removed from the boric acid, it forms metaboric acid. When two water molecules will be removed from two HBO2 molecules, so one water molecule from two HBO2 molecules, then we see the formation of B2O3, which we can call boric oxide, because this B2O3, or the boric anhydride, because this molecule is formed because of the anhydration or the dehydration of the boric acid. Anhydration or dehydration of boric acid forms this B2O3. That's why it is also called boric anhydride. Similarly, if you go to the organic chemistry, we can see the formation of carboxylic acid anhydrides. So the carboxylic acid on heating, what we see, the release of evaporation of one water molecule from two carboxylic acid molecules, and that's why oxygen of bond is formed, and so that we call the carboxylic acid anhydride in that case. So this anhydride means this is a form of water molecules were removed because of the excess heating of this boric acid. That's why this is boric acid anhydride. So orthoboric anhydride, and that you can remember this structure here, that from the borax. Now let's see this question: why is boric acid considered as a weak acid? As I said earlier, boric acid is a very weak acid, and why it is a weak acid? The reason is because it does not release H plus ion on its own. So it doesn't release H plus ion on its own. However, it has a vacant of p orbital, and so it can accept one OH minus group from the water, and also, and we know the ionization of water is not that facile. Its ionization constant is ionic product of water is very low, and so what we see, very few water molecules will be hydrolyzed because of the boric acid, and that's why very few number of excess H plus ion will be there into the aqueous solution, and thus boric acid behaves as a weak acid. So this boric acid receives OH minus ions from water molecules to complete its octet, and in turn releases H plus ions, and this H plus ion releases from the water molecules. It belongs to the water molecule. Now let's look into the diborane, and diborane is what? B2H6. Like alkane, we can also write borane. BH3, like CH4 is alkane. Methane, similarly you can say BH3 is borane. And now since two BH3 molecules they dimerize together, because BH3 is not very stable because of the Lewis acid character of BH3. BH3 also has 6 of electron, and it has a vacant p orbital. So two borane BH3 molecules they combine together to form diborane to have a certain gain certain amount of stability, and so this compound act that we see in the free form that exists is the diborane. The simplest boron hydride is the diborane. So this is the simplest boron hydride. It's actually BH3 in the dimeric form. So this is the simplest boron hydride, and it is prepared by treating boron trifluoride with lithium aluminium hydride in diethyl ether. This we call the lithium aluminium hydride. And if the boron trifluoride, so BF3, is heated with LiAl4, the lithium aluminum hydride, then this formation of diborane happens. So this B2H6 is formed plus LiF. This LiF will be formed, three molecules of LiF, and so three molecules of AlF3 will also be formed. So three molecules of AlF3, as you see, aluminium is available, still not used till here, and fluorine you can see 4 into 3. 12 molecules of aluminum fluorine. So 6 molecules will be here, 3 here. So, sorry. 3, 9 here, 3 into 3, 9, and 3 here. So 12 is already there, 12 is here. 12 atoms of aluminum fluorine are here, and 12 atoms of fluorine are also in the product side. 3 fluorine atoms here with the LiA, and 9 fluorine atoms with AlF3, and because we know AlF3, because of valency, you can easily find out what will be the chemical formula of aluminum trifluoride. So laboratory, this diborane is formed from the oxidation of sodium borohydride with iodine. This is sodium borohydride, NaBH4. The lithium aluminium hydride, as we saw this name, lithium aluminium hydride, so this name is also sodium borohydride. And when the sodium borohydride is oxidized with the iodine, and we see the formation of B2H6, and this B2H6 plus 2NaI plus H2, and this formation happens. And the industrial preparation of diborane is uh, like this BF3, when it reacts with the NaH sodium hydride at 450 Kelvin and above, it forms B2S6 plus 6NaF. So diborane is produced on industrial scale by reaction of BF3 boron trifluoride with the sodium hydride, and the sodium hydride on heating above 450 Kelvin, we see the formation of diborane plus 6NaF. Now coming to the properties of this diborane, and the properties of diborane is what? It's a colorless gas. So diborane is a gas. It exists in the gaseous state, and the gas is the colorless gas. It is highly toxic. Its boiling point is 180 Kelvin. 180 Kelvin is not, please remember, it's not degree centigrade. 180 Kelvin is very low temperature. So it's a 273, 180 minus 273 degree centigrade. So it catches fire spontaneously upon exposure to air. So it reacts very fast with the air. So it burns in oxygen, releases an enormous amount of energy. So B2H6, like other alkanes as well, so carbon compounds, hydrocarbons, the borane, diborane also releases, it also gets oxidized and releases enormous amount of energy, and that is why it catches fire spontaneously upon exposure to air, because air contains oxygen molecules. So B2H6 plus 3O2, it gives B2O3, is a boric oxide you can call, or the boric anhydride, because when the boric acid is heated to form this B2O3, then we can call it boric anhydride. But since this boric anhydride is not formed, boric acid is not heated to form this, so this we can call boric oxide or the boron oxide. Let's you can this see this structure, the boric oxide here. And the delta H for this reaction is minus 1976 kilojoule per mole, and you can see the enormous amount of heat is released because of the oxidation or the combustion of the diborane in presence of oxygen. So most of the higher boranes are also spontaneously flammable in air, because higher boranes also they get oxidizes, and in the air uh, uh, they get oxidized in the air as per the similar reactions. Also the water molecules and other things may change the number of molecules and the stoichiometric reaction, but the thing is the reaction will be the similar nature, and the similar nature means the boric acid oxide will be formed plus water molecules will be formed even with the higher boranes when they react with the oxygen of the air. So boranes are readily hydrolyzed by water to give boric acid, and this borane, as I said earlier, this boric acid, the preparation of boric acid can be made by hydrolysis of boron hydride, and see the diboranes are what the boron hydride. So diboron hydride B2H6, when it is hydrolyzed with water, so 6H2, it forms BOH thrice aqueous plus 6H2. The hydrogen gas will be released in this case, and we see the formation of the boric orthoboric acid or the boric acid. BOH thrice is what the boric acid or the orthoboric acid, and the orthoboric acid. This reaction with the halides I have shown with the hydride just now we have seen, and this BOH thrice is orthoboric acid, or H3BO3 we can also write. And so this BOH thrice aqueous plus 6H2 is what? The orthoboric acid. And the reaction of boranes that we see, one of the reaction here with the water, diboranes undergoes cleavage reaction with Lewis bases to give borane adducts. And borane adducts means the BH3L3. So what we see, the diborane is what? B2H6. It means it's a BH3 units. Two units of BH3 they combine together to form diborane. When a Lewis base is used, in that case this diborane actually splits its cleavage, it splits into two molecules, the monoboranes, two BH3 molecules, and in each BH3 molecule will now form an adduct with one Lewis base, and see one adduct that we see BH3L, where L is what? The Lewis base. The L is Lewis base, and B2H6 is divided into two BH3 molecules, and each boron now we see had a vacant orbital in BH3, and that vacant orbital will now be occupied by the lone pair of electrons of this Lewis base L. The examples we can see here is B2H6 plus 2NMe3. This is a Lewis base that we know. This is an amine. This is a tertiary amine, this NMe3, and this tertiary amine, we need two molecules of this tertiary amine to form an adduct with two BH3 molecules, because B2H6 is nothing but a dimer of BH3. So on splitting, on cleavage, it will form two BH3 molecules, and those two BH3 molecules will form adduct with one NMe3, and we see thus the formation of two molecules of BH3 NMe3. So, or if this is H3 NH3 ammonia, so we will see BH3 NH3, the ammonia boron formation here. And another example is B2H6 can also, in presence of carbon monoxide, this also behaves as a Lewis base because it has a lone pair of electron, and so this B2H6, it also reacts with two molecules of carbon monoxide to form two molecules of BH3CO. And BH3CO is a single molecule, single adduct. The coordination bond is there between one BH3 and one CO unit, similar to that we saw here in this case. One BH3 in the nitrogen's lone pair is now pushed into the vacant p orbital of boron to form this coordinate bond, covalent coordinate bond. Reaction of ammonia with diborane gives initially B2H6 2NH3. As I said, the ammonia earlier, like we saw here, the tertiary amine. So if this tertiary amine is nothing but ammonia, so what we see? We see initially the formation of B2H6 2NH3, which is formulated as BH2NH3 twice plus BH4 minus. So NH3 twice plus BH4 minus is what is this compound. On further heating, it gives borazine, and on further heating, what does it forms? It forms borazine. Borazine is what? If you remember the structure of benzene, so borazine has a structural similarity with the benzene. In the benzene, there are 6 CH units in a cyclic form. So 6 CH units there means carbon-carbon bonds are there with the 6 CH units. In the borazine, which is nothing but BH, 3 BH units and 3 NH units are there. And one BH and one NH units, if you look at it, it is isoelectronic to the CHCH unit. So Bn is what? Isoelectronic to CC bond. So Bn bond or Bn group is isoelectronic to CC because the number of electrons are same there. And so the BH and NH, when 3 units of each are there, they will actually have the structural or the isoelectronic property to that of the CH group. And so, like similar to CH, BH and NH, they can be arranged alternatively to form borazine, and this borazine we call inorganic benzene, and this structure is B3N3H6. So in the benzene structure, if you replace all the carbon atoms with one B, then N, then B, then N, then B, then N. So and now all the hydrogen atoms, you can keep itself at the same position, and so you will see the formation of borazine, and its structure is the aromatic structure similar to the benzene, and that's what we see. Now the 3B2H6 plus 6 ammonia molecules when and 3B2H6, because we see 3B2H6 when I am taking, it means I am taking 6BH3 units, and 6BH3 units, that it will react to form 3BH2NH3 twice this unit here, BH2NH3 twice plus and BH4 minus, and now on further heating this will give the borazine B3N3H6 plus 12 hydrogen molecules. And this reaction we see here, this diborane will be cleaved into this 1BH3, 1BH3 and 2 ammonia, and so one can also see the formation of BH3NH3, and this BH3NH3 is called ammonia boron, or NH3BH3 one can write ammonia boron. And this BH3, this unit, when this unit is broken from this place, if it is broken between these two BH3 units, and then each BH3 unit will interact with one ammonia molecule, and similar to that we have seen in this case. So it will form ammonia boron. Now we can see the cleavage of this bond also from this diborane. And when it breaks from here, now the two ammonia molecule will now come at the place of two hydrogen atoms, and this will be BH4 minus and this BH4 minus, and two ammonia molecules will now come to two B boron at two places at the boron atoms, these two corners, and so we see the NH3 formation. And NH3 formation, this molecule will have a plus here. Why there will be plus charge on this? Because of the ammonia, the nitrogen will have a plus charge, and here this is BH3, it will have a negative charge, and so this molecule is from this molecule. This I am saying similar to this structure is this, and on further heating it will form the borazine, which is B3N3H6. The structure, if you look at the structure of diborane, the structure of diborane is looks like this, and looks like this means what? The two BH3 units are there in the diborane. Now what can you do? You can write one boron and two hydrogen atoms of one boron, one BH3 in one plane, and in the similar same plane you can write one boron and two of its associated hydrogen atoms as well. Now one hydrogen atom from this BH3 and one hydrogen atom from this BH3 will be left over. So now this one boron and two hydrogen atoms of one boron and one boron and two hydrogen atoms of another boron, they will occupy the equatorial position. They will be on the same plane. And now the two hydrogen atoms that are there, initially they were in the one BH3 molecule. It was also on the same plane. However, because of the interaction, it will now be shifted to the out of the plane, and out of the plane, so one hydrogen atom will be above this plane like this BHH and HHB, this plane. The one hydrogen atom will be shifted below the plane, and one hydrogen atom of this, suppose this belongs to this hydrogen belongs to this boron, so it will be shifted above the plane, and this hydrogen belongs to this, it's shifted below the plane. And so now what we see, this hydrogen, although, and these hydrogens, they will actually make bonds with the both the borons. And initially what happened in the one BH3 molecule, there was only two electrons and one BH group. However, because of the availability of vacant p orbitals, this condition was not very stable, because the vacant p orbital was available, and it was also not a there was no complete octet of boron in the BH3. Now this hydrogen, this BH bond can also interact with this boron center, and so this BH bond, which has two electrons and two centers B and H, now once it will start interacting with the vacant p orbital of this boron, so another center will be involved, and now we see three center, two electron, and that bond we call the banana bond, and so it is a BHB. So this is the bridging hydrogen we call. Why bridging hydrogen? Because it is bridged between these two boron atoms, and there are four terminal hydrogen atoms as well. So we see these terminal hydrogen atoms, these terminal hydrogens, they are proper, they are normal covalent bonds. So these normal covalent bonds, and the length of these normal covalent bonds is 119 picometer, is 1.19 angstrom, and this angle is 120 degrees. So this angle will also be 120 degrees. This is 1.19 angstrom, this is also 1.19 angstrom, this is also 1.19 angstrom, and this angle is slightly lesser, and this angle, why it is lesser, this is also because it is shifted out of the plane, and this angle is actually not in the same plane angle, it's out of the plane angle. And also this bond, since two electrons are involved in bonding with the three centers, so this bond will be weaker than this normal BH bond, and so that's why the length of this BH bond, the bridging BH bond, is more. It's 1.34 angstrom or 134 picometer. So this is also 134 picometer. This is also 134 picometer. This is also 134 picometer. Although you may not see these bonds, the appearance, it may not appear to the similar level, but they are the same bonds, and this bond we call the banana bonding. And why this, just on appearance we have made it short and large, because one can understand one of the hydrogen belongs to this is just for the representation purposes. In reality, in normal molecules, in the nature, we don't see that much difference in the bonding. All the bonds, all the bridging BH bonds are 134 picometer. And this is the banana bonding that I have said, the banana bonding. Although there is a plane and out of plane structure that we have seen here, in this structure we have seen everything on the same plane, just to have certain understanding. And so these four terminal BH, one terminal BH bond, one, and four, and this two bridging BHB bonds that we see here. So this BH was there and dotted dot, which means the vacant p orbital of this boron, and this bond, these two electrons are now also interacting with this center, and so we see two electrons that was initially belonging to this is now also interacting with this boron center. So this electron will be delocalized along this line, and because of this delocalization we see the formation of similar kind of bond, and that we call the shape of the, because of the banana, we call the banana bonding. And this is banana bonding, one is here and one is also here at the center. So boron also forms a series of hydroborates, and the hydroborates that we know like BH4 minus, BF4 minus, BF4 minus is a different thing. The hydroborates means the hydrogen and the borate formation. So this BH4 minus is an example of the hydroborate, and this BH4 minus ion and tetrahydridoborate. This is a tetrahydridoborate because four hydrogen hydride groups are there, four hydrides are there. So tetrahydridoborate, tetra means four, of several metals are also known, and tetrahydroborate of many other metals are known. And the lithium and sodium tetrahydridoborates, as we know. So sodium that one of the examples that we have seen somewhere, like see here, NaBH4. This is also a hydridoborate of sodium. This is a hydridoborate of sodium. And so lithium and the sodium hydridoborate. So lithium and sodium tetrahydridoborates, also known as borohydrides, and that's we call sodium borohydride or lithium borohydride. So they are prepared by the reaction of metal hydrides with B2H6 in diethyl ether. So 2MH plus B2 2MH plus B2H6 gives 2M plus and BH4 minus, and this M is what, lithium or sodium, and this we call metal borohydride. So the metal is lithium, so we call lithium borohydride. Metal is sodium, we call sodium borohydride. So both lithium borohydride and sodium borohydride are used as reducing agent in organic synthesis, and mostly sodium borohydride is more general, more famous, and you can see, you will see some of its uh, reactions in the carbonyl chemistry when we will see organic chemistry. So the carbonyl chemistry, particularly when the when the aldehydes and ketones structures and their chemistry with the reduction we will study, we will see the use of NaBH4. So they are useful starting materials. This LiBH4 and NaBH4 are also the useful starting material for preparing other metal borohydrides. So one can use this as a starting material to form other metal borohydrides. And so this is what the some of the important compounds that we have finished. Let's now look into the usage of boron and its compounds. And boron, as if you remember, I have explained, it's a non-metal. A non-metal, and its melting and boiling points are very high. It's a, if it's non-metal, it means it's not a conductor. These kinds of properties that we know. So boron fibers. Now let's look into the boron uh, usage of boron. So boron fibers are used in making bulletproof vest and light composite material for aircraft because it's a light mm, element. So boron 10 isotope, because boron 9 there are many isotopes of boron. So boron 10 isotope has a high ability to absorb neutrons, and if something has high ability to absorb neutrons, then it can have use in the nuclear chemistry, and that you can understand if you know the nuclear chemistry a bit, how then in the nuclear reactors we sometimes need something which can absorb neutrons that are produced during the nuclear decay or the decay of a molecules, and so that one can control the number of neutrons. And once you control the number of neutrons, the chain reaction will also be controlled, and that how you can take energy in the controlled manner in the nuclear reactor. So to control a certain nuclear reaction, so the fusion reactions, we need certain types of neutron absorbers, and the boron 10 isotope has high ability to absorb neutrons. Therefore metal borides are used in nuclear industry as protective shields and control rods as well. The main industrial application of borax and boric acid, these compounds that we have just studied, borax and boric acid, is in the manufacturing of heat resistant glasses. Why heat resistant glasses? Because these materials as well, they are not conducting, and so the heat resistant glasses we can are like the pyrex. Also the glass wool. glass wool, we see the sheet structure of the glass wool or the fiber glasses. These boron compounds are used. The borax is also used as a flux for soldering metals as constituent of medicinal soaps. An aqueous solution of orthoboric acid is generally used as a mild antiseptic, which is a very mild acid, so it's also used as a mild antiseptic. So orthoboric acid, the aqueous solution of orthoboric acid. Now let's look into the usage of aluminium and its compounds. So aluminium is a bright silvery white metal that we know, and you might have seen as well the aluminium, which with high tensile strength. So aluminium also has a high tensile strength that we know. It has a very high tensile strength means what? One can form a very thin wire of aluminium. So it has a very high electrical and thermal conductivity. This is also known to us. On a weight to weight basis, the electrical conductivity of aluminium is twice that of copper. What does it mean? Suppose if the same length of wire, if you take a wire of aluminium and copper, same length of wire of aluminium and copper, and so what will happen, because the copper has a higher density, so because of the higher density copper wire will be thinner and the aluminum wire will be thicker, its cross sectional area will be more. And because this crack cross sectional area, because weight, we are taking same weight same length, and if same weight same length, because copper is having higher density, so the diameter of the copper wire will be less, and what we know, the resistance is inversely proportional to the cross sectional area. Cross sectional area is less, it means the resistance will be more. And so the aluminum wire with cross sectional area will be more, because of that resistance will be less for the aluminum wire, and we know the conductivity or the resistivity will also be less, and the conductivity is what? There is the reciprocal of resistivity, and that's why one can see the relation there. And so on a weight to weight basis, the electrical conductivity of aluminum is twice that of the copper. I hope you understand how it can be correlated, because these things we have seen in electrochemistry. I also might have read the similar thing into your electricity chapter that is there in the physics. The aluminum is used extensively in industry and everyday life. And some of the examples that we see, we also initiate earlier people use it as a in the utensils. So it forms alloy with copper. So aluminum forms alloy with copper, manganese, magnesium, silicon, and zinc. Aluminum and its alloys can be given shapes of pipe, tubes, rods, wires, plates, or foils, and therefore finds used finds uses in packing, utensils making, construction, aeroplane, and transportation industry. And these things, they are very well known to us. The use of aluminium and its compounds for domestic purposes is now reduced because of its toxicity, because aluminium is toxic in nature for human being, for the life, because aluminium is not there in the life in our body, that very a small amount of aluminium is required for us. And so the excess of aluminium, if you use as utensils and other things, it will go into your body, and so it will cause a toxic effect. And so its use is now prohibited, at least, or the at least its use is reduced in the domestic purposes. I'll stop here. I'll start uh, again in the next class. I'll start the group 4 chemistry of group 14 elements, some basic things, and few chemical reactions that we will see in our next class, that will be on the next Saturday. Okay, bye. I hope you enjoyed this lecture.